Hello everyone, my name is Aaron Standard, and today we're going to talk about distributing state reliably with Akka.Cluster.Sharding. This has been a very hotly demanded video from lots of experienced Akka.NET users, but if you're someone who's looking at building your first Akka.NET application, or you're trying to build the distributed system with .NET overall, this would be a really useful video to watch. So let's talk about what we're going to cover. First is, what is Akka.Cluster.Sharding? Second is, when should you consider using it? And third, we're going to talk about how cluster sharding actually works. So what are shard regions, shards, and entities? How do you actually go about using entity actors, and how do you design them properly? How does cluster sharding manage their life cycle? How do you actually code and configure shard regions? And then we'll talk a little bit about some of the mechanics of how Akka.Cluster.Sharding works. Namely, what does rebalancing look like? This is what happens when your cluster is scaling up or down, or if a node becomes unavailable and has to get kicked out of the cluster. How do we redistribute the state in order to make sure that it's evenly distributed, and so there's only exactly one instance of every business object inside the system? Then finally, we'll talk a little bit about observability. How can we actually keep track of how many different entities there are and where they distributed in our system? We'll talk a bit about that, and then we'll do a little demo at the very end. So before we get into Akka.Cluster.Sharding, it's important to remember that cluster sharding is built on top of Akka.Cluster, which is our tooling for being able to build highly available, decentralized peer-to-peer networks of actor systems. This is basically the basis for how to do horizontally scalable software with Akka.NET. So if you're not familiar with Akka.Cluster, you might want to watch the intro video, which we'll link to up here, on how Akka.Cluster works, so you can kind of get yourself familiar with the basics there. But for the time being, we're going to move on to talking about cluster sharding. So how do you go about actually installing it into one of your .NET applications? There's two ways of doing it. One is you can just install the Akka.Cluster.Hosting NuGet package. This uses Akka hosting, which is the modern way for being able to configure Akka.NET and integrate it into the Microsoft.Extensions ecosystem. We strongly recommend that. Or you can use the standalone Akka.Cluster.Sharding NuGet package. This is where all the actual sharding primitives are defined. So you can do either one of those and that'll work. Now, how Akka.Cluster.Sharding works and what it does. The first thing that Akka.Cluster.Sharding does is it's basically a tool for being able to distribute stateful entities transparently across your cluster. One entity equals one actor. That's always been a best practice. But what cluster sharding does a little differently is it automates the lifecycle management of those actors. It'll start entity actors automatically the very first time you attempt to message one, and it will shut those entity actors down again when they've been idle for 2 minutes by default. Next, we guarantee exactly one instance of each entity across your entire cluster globally. And this is even true during network partitions. So this is a strongly consistent, partition-tolerant way of being able to reliably distribute state across your application. Next, we guarantee an even distribution of state using our default distribution method out of the box. We use a consistent hashing approach for distributing entities across the cluster. We have a little video on that up here as well if you want to learn about how the math works behind that. But the basic gist of this is that no matter how many entities you have inside your system, we are going to guarantee mathematically an even distribution across all nodes. This distribution also supports things like adding and removing capacity to your network, so scaling your cluster up and down. And then on top of that, when we're in the process of, let's say, moving entities from one node to another, we actually have the ability to pause network traffic to those actors that are being moved so we don't lose messages. It's still technically possible to lose some if the message gets sent at exactly the right time. We'll do another video on Akka.Cluster.Sharding.Delivery, which is our tool that can solve even that problem as well. But for the time being, the built-in tooling out of the box is going to cover like 99% of your messages there. Now, just to provide a little overview of how Akka.Cluster.Sharding is organized, every single shard is going to be part of what's called a shard region. A shard region describes a discrete type of entity that we're going to distribute across our cluster. So in this case, this shard region is called items. The shards themselves are these parent actors that are basically just units of work that the shard region uses to reason about how to distribute state evenly across the cluster. These are built-in actors that you don't interact with directly. But these actors on the very bottom down here, the ones that are assigned letters, these are your entity actors. They represent an individual instance of a custom actor that you defined that is going to represent an item entity inside this system. So each of these are distinct entity actors, each with their own unique state. And this entity actor B will always belong to shard 1. But Shard 1 might not always be hosted on node localhost 99110. In fact, it might get distributed to a totally different node depending on what the topology of our cluster looks like. But this is sort of the taxonomy for how data gets organized in Akka.Cluster.Sharding. ShardRegion, then shard, then entity. So if we were to launch 2 more instances of this sharded process we just saw, here's what our state distribution might look like. We have 3 different hosts all running the exact same piece of Akka.NET code. They're all hosting the item shard region, but they have different shards. Shards 0 and 1 are assigned to the first node, 2 and 3 to the second, 4 and 5 to the third. And as a result of that, they're going to also own different entities. Entities can only belong to a single shard. We structurally guarantee that in the way the sharding algorithm is designed. And shards can only belong to a single host. We guarantee that also. So even though all of these nodes are running the exact same code, they all have totally different data and totally different entities. This is actually pretty important for kind of understanding the benefit of Akka.Cluster.Sharding. We are able to guarantee that there's exactly one of each entity inside the system. Therefore, that entity's state will always be consistent wherever it happens to be inside the network. So this is how Akka.Cluster.Sharding helps us maintain consistency inside our system by guaranteeing that all data for the same thing gets owned by the single actor that represents it. So what does Akka.Cluster.Sharding do? It allows us to create shard regions for each type of entity. You can have an arbitrarily large number of shard regions. If you have 12 different entities that need to be sharded, you'd have 1 shard region for each type. No big deal. All the state for each shard region is managed separately from each other. Next, the entities that are in that shard region are just actors. Typically, they tend to be persistent actors, actors that can recover their state after they've been put to sleep. So that's typically what they tend to be, but they don't have to be persistent actors. You could use your own custom state recovery mechanism if you needed one. The other thing that the shard region system does is that allows us to basically group entity IDs to shards. The same entity ID will always belong to the same shard ID. So that's mapping is stable, and it's typically defined using like a consistent hashing algorithm is the default way we do it. So that value is never going to change. We are able to determine the entity ID from the content of the messages you send through the sharding system. We're going to take a look at some source code for this in just a moment, but it's called a message extractor. And that message extractor basically has a little bit of pattern matching that helps us determine what is the identity of the entity that this message should be routed to. And usually that involves looking at things like, an ID property defined on the message. Something simple like that usually. We're also able to automatically manage the life cycle of entity actors. The first time you message that actor, it gets created. If you don't message that actor through the sharding infrastructure for up to, 2 minutes by default, the actor will be shut down. The actor references will all be invalidated. But the next time you send a message to the sharding system for that entity, that actor will be woken up and will resume processing messages again. This is very similar in spirit to how Orleans' virtual actors work. But this is just kind of a layer of how we implement that on top of Akka.NET. So Akka.NET supports all of those same, let's say, traits for being able to automate lifecycle management that Orleans does, but we also support things like local actors too. So anyway, for the rest of this talk, we're going to focus primarily on when you should use Akka.Cluster.Sharding and how it works, and what's the actual code and configuration you need in order to use it. So next up, when should you use Akka.Cluster.Sharding? If you have a lot of entities to manage, let's say hundreds or thousands or potentially even millions of entities, Akka.Cluster.Sharding is a great tool for being able to do that, particularly if your entity IDs are dynamic and theoretically unbounded. So good example, your customer IDs, if you're managing an e-commerce platform, are dynamic and unbounded. You don't want to have a universe of customers that is bounded for arbitrary reasons. You want it to potentially be unbounded. Or if you're doing something like IoT, for instance, maybe you can have devices connect and disconnect from your network. Those device IDs might be unbounded. So there's lots of different sort of parameters for kind of thinking about how big your universe is inside your application. Akka.Cluster.Sharding is designed to support dynamic and, in theory, infinite universes of entities. The other reason why cluster sharding is so amenable to this is that we guarantee an even distribution of work. If your workload is really small, you can shrink down the number of nodes that are hosting state, and that'll work fine. And let's say during busier periods, if you need to scale back up, Akka.Cluster.Sharding supports that just as well. It's all handled through our rebalancing mechanism, which we'll learn about towards the end of this video. Entities are designed to work intermittently over a period of time with Akka.Cluster.Sharding. So this means that those entity actors you're creating, I used the example of an order before, those order actors probably aren't going to be processing messages constantly. It's probably going to happen in little bursts. So what's going to occur with Akka.Cluster.Sharding is you're going to instantiate one of those order actors when something's happening. It'll go ahead and do a little bit of work, produce some responses, and then it'll wait for up to 2 minutes by default. And if it doesn't get any additional messages, the sharding system will shut that actor down and its resources will be freed back up into the available memory, CPU, and I/O for the rest of your application to leverage. That will help you keep a fairly consistent resource footprint over the life cycle of your application. So even though there might be lots of different entities being started and stopped all the time, if let's say you have an average amount of messaging at any given time, those should be totally different entities kind of doing work over the lifespan of your application. Akka.Cluster.Sharding supports that really well out of the box. Finally, if you need state consistency and scalability, Akka.Cluster.Sharding is a really good fit for that as well. So how does Akka.Cluster.Sharding actually work? Well, if we take a look at our 3-node cluster we had earlier, suppose I send a message to host number 1 where the entity ID that's on the message correlates to entity I, which doesn't exist at the moment. What's going to end up happening is that this shard region is going to determine that shard 5 is the owner of entity I. And we're going to route this message to the node where shard 5 is homed. The next step is the shard region running on host 3, which is where shard 5 is going to route the message to the shard, and the shard is going to see that entity I doesn't exist yet. So what will happen in this case is shard 5 will create this entity and will send it the message that we sent in step 1. So there's a couple hops involved initially, but this allows us to transparently message this entity actor I from anywhere inside our cluster. We don't necessarily have to go ahead and message it on node number 3, host 3 right here. We can send a message to entity I from anywhere inside the cluster using the shard region. So that's how the sort of messaging and activation process works for this entity actor. Now, what does the actual code look like for starting a shard region? This is using some of the Akka hosting syntax right here, where we're going to describe a sort of an entity, a key. This is how we're going to go ahead and pull the shard region out of the actor registry so other actors can use it inside our application. And the next thing you're going to see here is this little formula that accepts a string and returns props. Props are basically the properties of an actor. It's the formula we use for being able to instantiate actors in Akka.NET. So that's what we're doing here. What this little function does is S is going to be the unique entity ID. So we extract that from messages that are sent to the shard region. We can go ahead and use this little function to pass that entity ID into the ID of this actor. And if you're using something like Akka.Persistence, that entity ID might also be part of, let's say, your Akka.Persistence key that you use for recovering data. So that's sort of what this little function does. The next thing we're going to pass in is the message extractor. This is the piece of code the shard region runs for determining how to extract entity IDs from the messages we send. So that's what this is for, and we're going to see that code in just a minute. And then finally, we have the shard region configuration. This basically specifies where these entity actors can be hosted inside the cluster, how to store data about them, and also some other settings that we'll take a look at in just a moment. Now, when it comes to messaging entities, the trick to actually working with Akka.Cluster.Sharding is really simple. When we started that shard region on the previous slide, that shard region itself is an actor, and we get a reference back to it that we store in the actor registry. I can extract that actor from the actor registry using this registry.get method right here and just send that actor a message. That will go ahead and run that whole diagram we saw earlier of the shard region determining which shard this entity belongs to and routing the message to the appropriate node and then routing the message to the shard and then starting the entity actor. So messaging the actor reference gives us the ability to route messages transparently to the entity actor and to even start that actor if it doesn't exist currently. Now, it's also possible to message entity actors from outside of the shard region. So if you have another Akka.NET process inside your cluster, let's say you have a heterogeneous cluster that consists of different pieces of software all inside the same network, so Akka.NET microservices or other sort of service-oriented architectures. One thing you can create is what's called a ShardRegion proxy, which we're doing right here. We pass in the name of the ShardRegion's type. So in this case, it's items. We pass in the name of the Akka.Cluster role where the ShardRegion is held. Presumably, we're running on a different role. In fact, you can see that here. We're running on a front-end role, not a back-end role. But we also have to pass in the same message extractor the rest of the sharding system uses. So typically these message extractors, which I think we're about to see on the next slide, they're typically defined in a shared library that all the projects have access to. So a ShardRegion proxy is also an actor reference. And we can message the rest of the actors inside the ShardRegion the exact same way we would if we were inside the ShardRegion. It's just that this doesn't require the same level of infrastructure that the ShardRegion itself does. Namely, it doesn't need access to the underlying entity actor's type or anything like that. Now, finally, we have the message extractor itself. This is using the hashcode message extractor base class. What this base class does is it uses consistent hashing to go ahead and map entity IDs to shard IDs. Now, again, I'll remind you, if you haven't seen our video on consistent hashing, you can check that out here. But what consistent hashing means is that on every single node in our cluster, the same entity ID will always map to the same shard ID. That's mathematically guaranteed. On top of that, the IDs are so randomly distributed through the consistent hashing algorithm that we guarantee an even distribution of shards. And you'll get a chance to see that actually in our demo that we're going to fire up in just a minute. Now, finally, we have the number of shards inside our system. You can't really change the number of shards using the consistent hashing approach here after the cluster is launched. So you want to build in some headroom. In this case, we're planning on running a 20-node cluster. So I'm going to have 200 nodes, roughly 10 shards per node. That's kind of the rule that you want to use. You don't want to go crazy and have a massive number of shards because the sharding system is going to have to distribute that much data inside all of the different nodes that are in the cluster. You want to go ahead and try to reach a happy medium. 10 shards per node is usually a good figure. So if you expect your cluster to have, let's say, only, I don't know, a maximum of 5 nodes hosting the shard, you could probably get away with 50 shards. If you're planning on having a really big Akka.NET application where there might be 400 nodes all participating, then maybe you should have 4,000 shards. That would be a good number in that case. And then finally, we have the function for extracting entity IDs from messages. This is just a real simple pattern matching function. And if you've seen my video on pattern-oriented design with Akka.NET, which I'll link to here, we basically use these little marker interfaces that have identifiers on them. That way, any of the messages that belong to this specific entity, in this case it's an item entity, can all be really easily identified, and we automatically just forward the message to it based off its item ID right here. So this is what our hashcode message extractor implementation looks like for this item ShardRegion. Most message extractor implementations tend to be this simple. And then finally, we have the ShardRegion configuration itself. So in this case, we have 4 properties that are exposed. We have the role. The role is the most important. You always want to specify a role when you're working with Akka.Cluster.Sharding. This basically dictates where in the cluster, or really what processes in the cluster can host this particular type of actor. And it should only be, of course, the nodes that have the actor's code defined. So in this case, it's going to be our backend role. That's kind of like an important first-class feature of Akka.Cluster. Next, we have the passive idle entity after setting. This is where we determine how much idle sort of behavior from an actor should we tolerate before we shut it down. The default value for this is 2 minutes. That can be changed or configured by changing this setting right here. And then we also have this remember entities setting. If remember entities is turned on, it's turned off by default, then we're not going to passivate actors automatically at all. You'll have to manually shut them down using a procedure we'll talk about in another video sometime. But the other thing that remember entities does is it ensures that all entity actors are automatically started up automatically whenever a shard region is allocated onto a node. So those actors will all be started up immediately instead of us waiting for someone to send them a message. So this is really useful in cases where you have actors that maybe are receiving messages from outside of the shard region. Good example, maybe you have some entity actors that are connecting directly to a third-party data source like a market data feed if you're doing algorithmic trading. That might be a good use case where you might want to turn remember entities on. Generally speaking, you're better leaving it off and letting the sharding system manage it if you're not designing it so it can receive messages from outside the sharding system. And then finally, we have the state store mode right here. We'll have to talk about this more in another video at some point. But generally speaking, you should always try to use data here. That's going to require the least amount of infrastructure. And that's going to just use in-memory replication for the sharding system to be able to determine where shards are allocated at any given time. This is like a resiliency feature is what this is for. So I'd recommend using data. The default today is currently persistence, but we're planning on probably changing that in Akka.NET 1.6. But anyway, that's a setting that we'll talk about a little bit more in a future video. Now, the next thing I want to talk about is rebalancing shards. Rebalancing happens automatically when the cluster itself expands or contracts. So when new nodes join or leave, rebalancing means we have to move state from one node to another. So when nodes join the Akka.NET cluster, shards are going to gradually get rebalanced. We do this gradually because we don't want to abruptly move a bunch of state around in the event that actors are doing processing and are trying to persist things, etc. We want to go ahead and try to gradually move state over. So it's easy to do that when the cluster is expanding. However, when the cluster is expanding, we also pause traffic to the shard that is being moved. So that way, any of the messages that you're trying to send get buffered by the shard regions until we know that the shard has been successfully rehomed onto a new node elsewhere in the cluster. So that's something that we do to try to basically make sure there's no message loss happening while this is occurring. It's not 100% bulletproof, so it is possible for a message to get lost in flight. There's generally some timing constraints there. We have another tool that's already available in Akka.Cluster.Sharding called Akka.Cluster.Sharding Delivery, which can make the messaging durable, reliable, and retriable. We'll probably cover that in another video at some point, but that'll handle the 1% of cases that the built-in sharding system can't handle. Now, on top of that, when a node is leaving a cluster, shards are rebalanced immediately. This is because we can't stop, let's say, a process supervisor from shutting down a node in the cluster. We can buy some time and try to go ahead and move data as gracefully as we can, but we're on short notice here when this occurs. So we're going to try to very swiftly rebalance those shards on nodes that are leaving at any given time. And you'll see a demo of both of these in just a moment. Now, what does the rebalancing process look like? Suppose that host number 3 joins our cluster down below, and it starts up its ShardRegion items, but it has no shards at the moment. What's going to end up happening is we're going to one by one begin rebalancing shards onto this node. So we moved shard number 4 from host 1 to host 3. Now you'll also notice that shard 4 doesn't have any entity actors underneath it. By default, it won't, unless you have the remember entities setting turned on. We'll have to go ahead and receive a message for any of the entity actors that used to belong to shard 4 before they're recreated again in the future. So in a system where there's lots of frequent message traffic, that should happen right away. If the message traffic is somewhat infrequent, then no harm done. The actors probably weren't that busy anyway. Next, we're going to go ahead and rebalance shard 5 from host 2 to host 3. Now we have an even distribution of shards inside the cluster, and there's going to be no more rebalancing at this point. So rebalancing the cluster is a gradual process that tends to happen incrementally in order to make sure there's an even distribution of state. All the entity actors will be passivated, so they'll be gracefully terminated up here. Akka.Cluster.Sharding by default sends a poison pill into the actors' mailboxes. So that means that any messages those actors received before we were going to begin doing the rebalancing, all those messages should still get processed on the old node that they used to be on. And then when they get moved onto the new node, we're going to unpause message traffic for those shards. And any messages that were queued up between the shard knowing that it was being terminated and the shard being created again, those messages will all have been buffered by the shard regions, and those buffers will all be drained as soon as the rebalancing operation is done. So that's how we're trying to essentially preserve message traffic while the rebalancing is happening inside the cluster. Now, I want to talk a little bit about observability before we begin our demo. First, if you're a Phobos customer, Phobos has built-in metrics and dashboards and also tracing for Akka.Cluster.Sharding. So we'll actually see the Grafana dashboard for Phobos in our demo here in just a second. The other tool you're going to see me use is Petabridge.Command. Petabridge.Command is a free CLI. It has a cluster sharding command palette that will allow you to go ahead and keep track of where shards are allocated inside your cluster. If you want to figure out where a specific shard ID is in your network at any given time, the cluster sharding command palette can help you do that. So without any further ado, let's take a look at a little demo and actually observe how well Akka.Cluster.Sharding actually functions in the real world. All right, so this is the code sample that I have running here. I'll include a link to this in the description. This is all open source. This is the little Phobos dashboard that I'm running for this cluster right now. So there's a total of 6 nodes. I believe it is 3 front end, 3 back end. Let me just double check that. Well, it's only going to show me the total size of the cluster here. But yes, I believe it's 3 front end, 3 back end. Let's see, the back end is doing about 1.26 thousand requests per second. All right, looks good. And then on the front end, go ahead and open this up. On the front end, we're doing like 100 requests per second. So the front end's doing a lot less traffic than the back end is. And if I scroll all the way down here, we can go ahead and take a look at the shard distribution data. So I've got 3 nodes, these 3 backend nodes right here. I think I'm hosting up to 200 shards total. So if I totaled these 3 numbers up, that'll give me 200. And each one of those shards has roughly 2,400. Well, all the nodes have roughly 2,400 actors each. So a relatively even distribution. If I scroll back up here to my actor metrics and I take a look at, this is the total number of alive actors in each process. There's a little bit of fluctuation. We have some random messaging going on and some actors shutting down, starting back up. You can see that there's roughly about, 2.5 to 2.6 thousand actors per node on here. You can see, yep, exactly 200 shards. And then I can see, it looks like roughly 7,200 item actors. Those numbers will fluctuate up and down as actors start and stop using the cluster sharding mechanism. All right, all that looks pretty good so far. All of the code that I'm using to run this demo is exactly what you saw on the slides earlier, so we won't rehash that again. One thing I did want to do is I'm going to go ahead and try to scale my cluster up here. Okay, so I'm going to scale my number of sharding replicas. I'm running 3 nodes in this little Kubernetes cluster right now. Let's go ahead and ramp it up to, you know what, let's go ahead and do, why not? Let's do 10. Okay, so this should add 7 more backend nodes to my cluster. And one other thing I can go ahead and do is I can go ahead and use kube control exec. So I'll go ahead and do exec, I think it's what, backend 0, pbm cluster show. All right, so this will go ahead and show me that I've got 8 total nodes in my cluster, 1 more joining. I've got my 3 front-end nodes here. So we're having a bunch more nodes joining the cluster. If I scroll up, you can go ahead and see this on my little Phobos dashboard here. So we should reach a maximum size of, I think, 13 total nodes. Kubernetes kind of gradually spins them up one by one, so that all looks good. And we should see message traffic scale up a little bit too. Each one of these backend nodes is going to start applying a little bit more messaging pressure. So this value should go ahead and start ticking up as well. As yeah, there we go. We're up to 2,000 messages a second going over the network right now. All right, pretty cool. And you can go ahead and see here that we have our 3 sort of original nodes have like, 2.7 to 2.8 thousand actors each. The newer nodes that are starting up have like less than 100 right now. So that's just part of the scale up process. And if I scroll down here, we can see some of the shard rebalancing. This is what I really wanted to show. So we have 65, 66, 66 shards on the old nodes here, but we've gradually begun rebalancing some of the shards onto these newer nodes. And you can see that some of the newer nodes also have entity actors that are all starting up. This rebalancing process, since we had 200 shards that were originally concentrated on 3 nodes, and now we're trying to redistribute them to 10, this will take a little while for the rebalancing to happen. There'll probably be one rebalancing operation that happens roughly every 30 seconds or so. So that might mean that it might take maybe up to an hour or so for all these shards to be fully rebalanced. Now, if I shut one of these nodes down, you would see all of those shards instantaneously rebalance. In fact, I'll go ahead and do that in just a minute here. Next thing I want to go ahead and do is we're going to use one of the cluster sharding commands from petabridge.command. So I think it's the region stats command. I'm going to pass in R items. So this will give us an exact breakdown of all the different, let's say, shards and entities inside our system. So I have up here, looks like it's reporting that I have 64 shards and just under 4,000 entities. By the way, the reason why these numbers might be slightly lower here, this is based on a bit of an average that's being reported in by Prometheus. So this data lags a little bit, whereas this data is like instantaneous. It's all point-in-time representations. So eventually this data will all kind of level out. There's also more entity actors being activated right now because the messaging throughput of the cluster is increasing. Let's see what it looks like now. Yeah, it's at 2.7 thousand messages per second. This value will also keep going up, by the way. And you can see the number of actors in the system going up as well. So those values, oh, there we go. Now these values are refreshed and they kind of look like what we're seeing in petabridge.command. That all looks good. And I'll go ahead and run this one more time. Okay, so you'll see that we have 3 nodes with 62 or 63 shards apiece and a bunch of nodes that have 2 or 1 shard. I'm going to go and connect to, let's say, backend number 2. And I'm going to go ahead and cause this node to leave the cluster. That should cause all of these shards to immediately get rebalanced. So let's see what happens here when I do that. All right, that node is now leaving the cluster. It's exiting, removed. Okay, the leaving is complete. I'm going to go ahead and do a little readout of what our sharding looks like now that that node is left. Lo and behold, every single one of these nodes now suddenly has 11 shards on it, except for node number 2, which got rebooted by Kubernetes. And yep, you can see here, Prometheus just went ahead and set that value back down to 0 again for entities and shards. So that's Akka.Cluster.Sharding rebalancing working in real time to go ahead and redistribute state across the cluster as we're scaling up and as we're scaling down. So the petabridge.command palette can help you really play around with that a little bit locally on your machine. And Phobos can really help you monitor that at large production scale like how we're doing here. This is actually a relatively small cluster in terms of the total number of nodes and the total number of entities here. I've got users of Akka.net that have several million entity actors all running at once, not the, I guess we have 10 or 12,000 here at any given time. So if you're interested in learning more about Akka.net and learning more about how to leverage distributed systems with it, please go ahead and subscribe to our channel and like and leave a comment below. Thank you very much.